Hello everyone, welcome back to our channel, and in today's video live stream we are going to be continuing with our series of electronics and telecommunication for UPSC Engineering Services Examination 2024. So we are done with our digital electronics series, and today we are going to move on and look through the analog communication syllabus, and this is going to be the lecture 1 for analog communication. So throughout the series of our lectures, we are going to in brief going to have a quick revision for our UPSC Engineering Services Examination 2024. So initially we will look at the theory part, and then we will move on to solving the different MCQs or practice questions and the previous year questions as well. Right, so let's get started. So very first, let's start with the introduction. The different let's first understand what communication is. So basically, it is nothing but exchange of information between 2 points through establishing a connection. So you can read it over here. It's a process of establishing connection or link between 2 points for information exchange. And this thing over here is the block diagram for our communication system. Our communication system consists of different blocks. The very first one is the information source, right? The information source is nothing but the group of messages or whatever message from which it originates. So you can see this is our first block, information source. Then we have a transmitter, right? After the transmitter basically like the objective of the transmitter block is to collect the incoming messages, modify it in whatever needed format, and then transmit it to the channel, right? Then we have the receiver. Yes, so what the receiver does is basically the receiver's function is to reproduce the original message. Yes, this is also known as demodulation or detection, right? Then you can see these are the definitions written over here. So basically the channel is nothing but the physical medium which connects the transmitter to the receiver. It can be wired or wireless. If it is a wired channel, then we can see the cable, fiber optic, etc. And if it is wireless, then it is space, atmosphere is the channel. Then this we have the receiver block. Now let's understand what basically signal means, or message or information. So signal, it is nothing but a physical quantity that is going to vary with respect to time or space, right? So in electric waveform which carries a signal, like for example, this is a signal m of t. M of t is equals to a cos omega t, right? So this is an example of a signal, electrical waveforms which is carrying a information, right? Now let's look at the types of signals. So these are the types of signals. Analog signal, which is also called as a continuous signal, which varies with respect to time. Yes, which varies with respect to time is called as an analog signal. Then we have the digital signal. It is the signal which contains only two discrete amplitudes, right? Say for example 0 or 1, right? It is called as a digital signal. Okay, then with respect to the communication part, we have different types of signals. The very first one is the baseband signal, and the second one is the band pass signal, right? So basically the message signal that is generated from the information source is known as baseband signal, right? This baseband signal may be a combination of one message, two messages, or more than two messages, right? So we can also say that if the signal contains zero frequency or near to zero frequency, it is also called as baseband signal. So as I told you that the message signal that is generated from the message information source is also called as the baseband signal. So these are some examples like voice signal, audio signal, etc. Right? Then next thing is called as the baseband pass signal. So if the signal contains band of frequency far away from the base or zero is called as band pass signal, right? So this is the difference between baseband signal and band pass signal, right? So examples AM, FM, we are going to study all these signals in detail, right? Now what is a message? So message, it is nothing but sequence of symbols. And what is information? The content of the message is called as information, and it is inversely proportional to the probability of occurrence of the signal. And information is measured in bits, decits, and nats. Right? Now, let's move on to the first very important concept, that is called as modulation. So how do you define modulation? See, it can be defined as the process by which some characteristics of a signal called as carrier is varied in accordance to the another signal called as the modulating signal. Right? The carrier signal frequency is greater than, okay, but before that, see, so basically if this is our carrier signal and this is our modulating signal, right? So what is done, there is, it is the basically process by which some characteristics of a high frequency carrier is changed according to the instantaneous value of the baseband signal, message signal, or the modulating signal. Right? Sometimes the message signal can be called as modulating signal, or sometimes the modulating signal is also called as baseband signal. So this is a silly mistake that some of the students make while solving the questions in the exam, right? Okay. So now next, these are the different types of modulation that we are going to study. First one is continuous wave modulation and pulse modulation. Okay. Under the continuous wave, we are going to have amplitude modulation and angle modulation. So angle modulation is of two types: frequency modulation and phase modulation. Right. Whereas in case of pulse modulation, we have the analog modulation and the digital modulation. This is also we are going to study in further lectures, but in today's lecture we are going to specifically focus on the continuous wave modulation. Right? So let's get started. First one is the amplitude modulation. Now, amplitude modulation, that means the name says it all. We all know what amplitude means. It is nothing but changing the carrier value in accordance to the information signal, right? In case of amplitude, we are going to change the amplitude of the carrier signal in accordance of the modulating signal. So these are the two important terms. Amplitude will change in accordance to the values of modulating signal. So this is nothing but amplitude modulation. Next is frequency modulation. So in case of frequency modulation, what would change? Yes, the frequency of the carrier will change in accordance to the values of modulating signal. And when I say phase modulation, the phase of the carrier signal will be changing in accordance to the modulating values of the modulating signal. Now let's look at some of the benefits of or why do we need modulation. The very first thing is to reduce the length or the height of the antenna. Next thing, it might be used for multiplexing. The another important is to reduce the noise effect, right? And the last, or the one of the most important benefit is also to reduce the size of the equipment, because this would help us to reduce the size of the equipment, right? Now let's look at and study the amplitude modulation in detail. So what is amplitude modulation? It is nothing but defined as a system in which the maximum amplitude of the carrier wave is made proportional to the instantaneous value of the modulating signal or the baseband signal. Right? So you can see there are two signals over here. This is the baseband signal, also called as our information signal, and this is our carrier signal. Right? Now carrier signal is a high frequency signal. Right? Now we are going to change the amplitude of the carrier signal in accordance to the baseband signal. So this is what is produced. You can see over here, this is what is produced, right? This figure is nothing but called as our AM signal, right? Now let's get into and study the different equations. Now the very first thing, the carrier signal, the carrier signal over here is given by C of t, right? And our modulating signal or our information signal is given by x of t, right? So the value of C of t or the carrier signal is nothing but AC cos omega t, and our information signal or baseband signal is AM cos omega mt, right? Now what is this A? A is nothing but the amplitude. Okay. Now where, see, you can see over here also it is written AM is nothing but amplitude of baseband signal and AC is nothing but maximum amplitude of the carrier signal, and omega is 2 by f. We all know that, right? Now let's understand the standard equation for the amplitude modulation, right? So the standard equation for amplitude modulation is given by this. So standard, it is nothing but AC cos omega 2 f t into bracket 1 plus ma into cos 2 pi f t, right? Where ma is nothing but the modulation index, and modulation index of is given by am upon ac. And what is am is nothing but amplitude of baseband signal, and ac is nothing but maximum amplitude of the carrier. So modulation index is nothing but the ratio of amplitude of modulation signal divided by amplitude of carrier signal. Now this is the time domain representation of EM signal. You can pause the video and take a screenshot of this, right? Now, yes. Now this is the modulation index that we have already seen. So modulation index is also called as depth of modulation, and it is given by AM by AC. Now, depending upon the value of the modulation signal, we can say there are three types of AM, yes, with respect to modulation signal. So when the value of AM is less than 1, we say there is under modulation. When AM is equal to 1, it is called as critical modulation. And when the value of MA or the modulation index is greater than 1, it is called as over modulation. I will show you the different types of modulation now. Yes, you can see over here, this is under modulation. That means the value of modulation index is less than 1, right? Then this is critical modulation, where the value of modulation index is exactly 1, and this is over modulation, where the value of modulation index is greater than 1, right? So this is nothing but the different types of modulation AMs depending upon the modulation index, right? Now, yes. So how do we define the modulation index? Over here I have missed one slide. But how do we define the modulation index? It is nothing but defined as the measure of extent of amplitude variation about an unmodulated maximum carrier. And it is mathematically represented as this. Right? So this was about the modulation index. Right? Now, the minimum value of amplitude the minimum value of an amplitude modulated wave can be given as A minimum is equal to AC minus AM, right? And the maximum value of amplitude modulated wave is nothing but AC plus AM. These are the two formulas. You can also note it down in your um notebooks, right? Okay. So this was about the modulation index, right? Now let's look at generation of AM wave. So basically the device that is used to generate amplitude modulated wave is known as amplitude modulator, right? And there are different types of amplitude modulator. The very first one is the square law modulator. So basically a square law diode modulation and a switching modulation are examples of low level modulation, right? Because this kind of circuit or a square law, these kind of circuits are suitable for low voltage level. So basically there are two ways of generating the AM wave. First one is low level AM and second one is high level AM, right? Under the low level AM there is one method, that is the square law um, generator method. So basically this circuit consists of a non-linear device which could be a square law or diode, then we have the band pass filter, and then we have the carrier source and the modulating signal. Right? Now let's understand the generation of the AM wave. So the modulating signal and the carrier signal are connected in series with each other, and the sum of voltage is applied to the input of the non-linear device such as a diode or a transistor. Right? Now you can see, I'll show you the block diagram. Yes, this is the switching modulator. You can see this is X of t. This is nothing but, I'll change the color. It's not visible, I guess. Yes, now it's visible. This is X of t, that is nothing but our information signal. This is our carrier signal, right? Now these are connected in series, and the sum of both of them is given to the input to a non-linear device. In this case, they are using a non-linear device, which is nothing but a diode, right? Now, the output of the diode is again passed through a band pass filter, right? So in this case, instead of a filter, we have a resistor over here, because this is a switching modulator. Let me show you a block diagram. Yeah, you can see over here. So in this case, there is a diode that is used as a non-linear device, and then the output of this diode is, so you can see this is the carrier signal, this is the modulating signal. They are connected in series. Then the sum of their output is given is given as input to a non-linear device. It could be a diode or transistor, and then the output of this non-linear device, in this case it's diode, it is given to a filter. You can see this is a filter over here, right? And then the filter is again, then the band pass filter, and then the result that is produced, the output, is nothing but our AM wave, right? So let us see it in the form of equation. Now you can see this is the result, xt plus x of t. This will be the output of, our non-linear device. Yes, and then when it is passed to the filter, we would have the output signal, which gives us the AM wave, right? Now in here, it is not visible clearly, but I will give you the equation in the further slides, right? Okay, till here just remember the block diagram that we have seen, this one, right? Now, next is nothing but detection of our AM, right? So now there are basically three types of detectors. The first one is square law detector, envelope detector, and rectifier detector. Now, a square law modulator is a low level amplitude modulator. Similarly, a square law detector will also be a low level amplitude detector, right? So this is the block diagram of a square law. Now this is also very similar. So what basically it is done at, the input is that is generated, the AM that is generated, it is given to a non-linear device, right? And it is, this non-linear device is used to detect the modulating signal, right? So you can see over here, this is our AM wave. This is connected to our square law, right? Right, so you can see over here, the amplitude modulated wave is given to the square law. So we can say V2 that is generated at the output of the square law is this, right? And then this is passed through a square law device, right? And then what happens is, in order to obtain the original message, we need to pass it through a low pass filter. So at the end of the low pass filter, this is the output that we get, and this is our original modulating signal, right? So very simple. In the previous, when we saw the square law modulator, in that case a non-linear device is fed to a band pass filter, right? But now in case of a detector, we are passing it through a low pass filter, right? Low pass filter, right? This was about the detection of an AM wave, right? Now this next one is nothing but the second type, that is an envelope detector, right? So the AM wave is fed to a detector diode, and then there is a filter capacitor or that helps us filter out the unwanted and retrieve the original signal, right? So basically the standard AMA wave, it is applied to the detector over here, you can see, right? Now In every positive half cycle, the diode will be forward biased and then it will charge the capacitor over here, right? Now, when the capacitor charges over here, the capacitor charges to the peak of the input, the diode will stop conducting, right? And then the capacitor will discharge through R, right? The capacitor will discharge through R. Then again this process will be repeated till the capacitor is discharged. Then again we will have the positive side. The diode will conduct, again the capacitor will charge and then discharge through R. So in such a way you can see through this charging and discharging we have the wave that has been generated, right? So this is nothing but an envelope detector. So this is just the process that has been written over here. Right? So in this manner, there is detection of AM wave that has been done. Right? Now let's move on to the different types of AM. One second. Yeah. So there are different types of AM. This is amplitude modulation. The very first one is double side band suppressed carrier. Suppressed carrier. This is the first one. Right? Then we have single side band suppressed carrier, right? This is the next one. Then we have the vestigial sideband, right? So these are the main three types that we are going to be studying over here, right? So you can see over here the very first one is a DSB-SC. That means the double sideband suppressed carrier signal is obtained by multiplying the modulating signal with the carrier signal. So one second. Before that, okay, let me explain to you what this is. So the like in the modulating signal which contains like no carrier but it has two side bands is called as double sideband suppressed carrier modulation basically, right? So I will show you the diagram over here. So if this is the frequency spectrum, this is the frequency spectrum, this is the carrier signal frequency FC, and this is the upper side band which is nothing but FC plus FM, and this is the lower side band. This is nothing but FC minus FM, and this is the frequency of the carrier. Right? This is the frequency spectrum diagram that we are all aware of. Now when this carrier is suppressed, we have two side bands, that is the lower side band and this is the upper side band, right? So basically why the carrier is suppressed and only side bands, why only the side bands are remaining in the spectrum, that it has some advantages. That's why we are suppressing the carrier. The very first one is, we all know that it contains two side bands and there is some power efficiency that is happening, plus there is power saving that is happening, right? So to save the power of the spectrum, we are going to require less power since the carrier is being suppressed. So that's why we go for the double sideband suppressed modulation, right? Now how is it obtained? It is very simple. We use a product modulator. Yes. Now, when you give the input as x of t is nothing but our modulating signal, and our c of t, that is nothing but our carrier signal. When they are multiplied together, we get an output modulated signal, which is nothing but our double sideband carrier signal. Now, this signal is then propagated through the channel, right? Now there are different types. The very first one is the balanced modulator, right? Now in this case it consists of two amplitude modulators, AM1, you can see this is AM1 and this is AM2, right? Now it consists of two carriers, two AM modulators, and it consists of one carrier oscillator, right? Now the message signal is directly applied to AM1, right? And then the same message signal, there is a 180-degree shift that is done to the original signal, and then it is applied to the second modulator, right? So if the input, therefore the input to the first modulator is x of t, and the input to the second modulator is nothing but minus x of t, right? Right, minus x of t. Now these two outputs, okay, now then the two outputs of these modulators, in this case we are considering, say, the output is y1 of t in case of am modulator 1, and it is y2 in case of AM modulator 2. Now these two outputs, there is a subtracting operation that is applied, right? So these two outputs are applied to a subtractor. You can see this is a subtractor over here, yes, and then the output that is given, the final output that is obtained, that is nothing but a double sideband suppressed carrier. So you can see in this very simple manner what we have done. There are two AM modulators, AM1 and AM2. The message signal to the first one is x of t, and the second one, second input to the second modulator is nothing but a 180-degree shift. Right? So you can see, let's look at the operation. So you can see, yes, the carrier is applied to both the modulators, but the message signal 1 applied is x of t, and the modulator 2, input signal to modulator 2 is nothing but with a phase shift of 180 degrees, right? And then the output, see, this is the output of both the modulators, then they are applied to a subtractor, which gives us the final output, that is nothing but a double sideband suppressed carrier. Right? Now, the next one is nothing but a ring modulator, right? So basically it has two modes. The first mode is without the modulating signal, and the second mode is with modulating signal. So in case of mode 1, what happens is the carrier, that is C of D, it is nothing but positive. So in this case, basically, let me show you the diagram. Yes, so this is the diagram. Okay, there are four modulators, which four diodes that have been connected in this manner. One, two, these are connected diagonally. Right. So what happens in this case is the diode 1 and 2. That means these diodes you can see in blue. These diodes are forward bias, and these diodes are in reverse bias condition. Yes, when the carrier input is positive, right? But if the ring modulator will be 0 in case the carrier is negative, because then the diode D1, D2 are reverse biased, and diode D3, D4 are forward biased. So this is the output. So therefore the output of the ring modulator will be 0. Right? Now, the second mode, when the modulating signal is present. So during the half cycle, the first half cycle, that is the positive half cycle, diode D1 and D2 will be on, and during the secondary of the T2, that in that case the secondary of T2 is directly applied to the primary of T1. So you can see over here, see, this is T1 over here, and this is T2. So secondary is applied to T1, and primary is applied to T2. So you can see this is T2 over here. This is the primary side. Sorry, yeah, this is the secondary side. This is the primary side, and this is the secondary side. Right? So therefore the output will be positive. And during the negative half cycle, D3 and D4 will be on, and it would produce a positive voltage. Right? So this is the block diagram. You can see in the very first cycle, see, this is these green diodes, this green color is nothing but D1 and D2 are on, and this is the blue color over here is nothing but D3, D4 are on, right? This is our original signal, and this is our carrier signal, right? So during the positive half of the cycle, D1 and D2 are on, right? And during that period, D2, D3 and D4 are producing a negative output. Similarly, during the second cycle, during the second positive half cycle, D2, D3, D4 are producing positive output. D1, D2 are producing negative output. So in this manner, using the ring modulator, there is a double sideband suppressed carrier output that has been produced. Right now, let's move on to see. Yes, this is the frequency spectrum of a double sideband suppressed carrier. I already showed you this. If this represents the FC is nothing but our carrier frequency, then this will be FC minus FM, this will be FC plus FM. This is nothing but lower side band, and this is nothing but the upper side band. So in our case, the carrier has been suppressed, right? This is the frequency domain representation. Now let's move on to the demodulation of a DSB-SC. Right? Very simple. The input is there's a product modulator, which nothing but the DSB-SC over here. This is the DSB-SC. DSB-SC is given as input to one to product modulator, and then it is multiplied with a signal using the local oscillator, right? Then there is an output produced, and then this output produced is given to a low pass filter to obtain the original signal, right? To obtain the original signal. So this is the block diagram of demodulation uh, of a DSB-SC. Now let's move on to the next thing, single sideband suppressed carrier. So you can guess it from the name only. So this is the modulation process in which only one sideband is transmitted with suppressed carrier is called as single sideband carrier. In case of double sideband, you do remember the frequency spectrum diagram, right? So in this case, only this carrier will be suppressed, and only one single band, lower band or upper band, any single band is being transmitted. So let's look at the generation of SSB. The very first method is the filter method, or it's also called as the frequency discrimination method. So basically, there is DSB-SC signal that is being produced, right, from our message signal and carrier signal using the product modulator, and then there is a band filter that helps us suppress the single band. Yes, and then it therefore it produces a single sideband wave at the output. Right, this is the filter method in which we are going to use a band pass filter. Right, now next is nothing but the phase method or the shift method. Now in this case, what happens is there are two product modulators that are being using, right? In case of the first product modulator, the input is x of t. In case of the second product modulator, there is a 90-degree phase shift to the original signal, 90-degree phase shift to the original signal x of t, and it is fed as the input to the product modulator 2. Now in case of the second input to the product modulator, that is our carrier signal, for the product modulator M1, the carrier signal is given as x of t. But in case of the second modulator, there is a 90-degree shift added to the C of t as well, right? And then the both the output, say in this case it is yt, y1t, and in this case this is y2t. So they are they are given as input to an adder. There is an addition operation that is happening, and then in such a manner there is a SSB signal that is being produced. Right? So this is nothing but SSB, that is single sideband carrier. Right? Now let's look at the next. That is nothing but vestigial sideband. Now basically this is used to transmit video signal with large bandwidth signals containing low or very high frequency components. Right? Now in this case, what happens is there is a so basically it is not possible to suppress one complete sideband, right? So very low frequency contains most of the useful information, and any effect to the to completely suppress one of the sidebands would result in phase distortion at these frequencies, right? Therefore compromise has been made to suppress the part of the sideband. Hence vestigial sideband signal contains one full sideband and part of the other band, right? It will contain one whole sideband and part of the other band. Right? So how do we do it? Let's look at the block diagram of VSB modulation. So here we have a product modulator. Yes. So over here we would produce a DSB-SC, double sideband suppressed carrier. Right? Now this is given to a sideband filter. So this sideband filter will suppress one of the sides and therefore it would produce a VSB signal. Right? Now this is nothing but modulation of VSB. Now let's look at the demodulation of VSB. So the VSB wave is given fed to a product modulator with a carrier oscillator, and this is given to a low pass filter which helps us produce the original information. Right? Original information. So this was about VSB modulation. So what did we study till here? So we have seen how a double sideband suppressed carrier signal is produced. Then using the same principle, we have seen how a single sideband suppressed carrier is produced. Its modulation and demodulation. We have seen both. Yes. Then again, using the same DSB-SC signal, when it is fed to a passband filter, DSB is produced. Right? And then we have seen the modulation of all three, and we have also seen the demodulation of all three. Right? So in this manner we have seen the different types of AM: DSB, SC, SSB-SC and VSB. Right? Now in the okay, okay. Now before that, let me just draw a table where we would compare the three. Okay, this is DSB-SC, this is SSB-SC, and this is vestigial sideband. Yeah. Right? Now in this case, firstly let's talk about the carrier signal. The carrier signal is fully, one second, the carrier signal is fully suppressed. The carrier signal is fully suppressed. In case of SSB, the carrier signal is fully suppressed. And in case of VSB, it is not applicable. Okay, carrier suppression is not applicable. Right? Now, in case of DSB-SC, let's look at the sideband suppression. What about the sideband? In this case, it's not applicable because both the sidebands are present. In case of SSB, one sideband is suppressed. One sideband is suppressed in case of SSB. Right? Now, next, in case of VSB, one sideband is suppressed. One sideband is suppressed partially, not completely, it is partially suppressed. But in case of SSB, one sideband is fully suppressed. This is the difference. Right? Okay. Now let's look at the bandwidth. Let's look at the bandwidth. The bandwidth of DSB-SC is given as 2 FM. The bandwidth of SSB is given as FM, and the bandwidth of VSB ranges from FM to twice FM. It ranges from FM to twice FM. Right? Now, let's look at the number of modulating inputs. Number of modulating inputs. In case of DSB-SC, we have one modulating input. In case of SSB, we have one modulating input. But in case of VSB, we have two modulating inputs. Right? So this is a quick difference between DSB-SC, SSB-SC and VSB-SC. So with this note, let's end the lecture over here. If you have any doubts, you can put it in the comment box. The link for the Telegram channel is also given in the description box, description below. The Telegram channel is given, and the live playlist link is also given. Do subscribe to the channel because we are going to be posting such more sessions for a quick revise of for our ESE 2024 prelims. And then we're going to also have sessions on solving PYQs and MCQs, practice MCQs as well, right? So I'll see you all in the next video. Till then, revise and understand, and if you have any doubts, you can comment, and you can also message us on Telegram. So thank you so much everyone for watching. With this note, I will end the session over here today. Thank you.